we have a cross section here, and we liked in a rectangular beam, so then I picked the rectangular beam. So then we have width is B, height is H, and of course neutral axis is at the center, right? And the way that we calculate Q is we take a small element like this, which is shaded area. So then I'm going to call this area as A prime. And the distance from the neutral axis to the center of this shaded area is Y bar. And then bottom of this shaded area is Y. Then what I can do is Qx is equal to integral A y dy, right? dA, right? From definition. And which is, we have shaded area A prime times distance Y bar. Make sense? Then what we can do is we can calculate Y bar. Y bar can be calculated Y plus H over 2 minus Y, which is this, divided by 2. This is Y bar. And A is H over 2 minus Y times width B. Then we can simplify this. 1 over 2 and this term times B. So this is a function of Y, right? So Q is a quadratic equation or linear equation? Anyone can answer in the chat box. Is Q quadratic equation of Y or linear equation of Y? Quadratic? Alexander says quadratic. Of course, this is quadratic, right? This is a second order term. When you have, yes, Cesar, this is quadratic. And when you have a quadratic, this is not linear line, right? This is curved. So what this means is your Q is curved relation depending on Y location. This is very different from your, so then your tau is a function of Q, right? So then let's go back to the shear formula. So then your tau, shear force, is a function of your Q. So then I is constant, T is constant, V is given at location X. Then Q is quadratic, which means your shear distribution is quadratic, which means curved, depending on the location of Y. This is very different from your bending stress formula. Bending stress formula was a sigma is equal to my over I. So m is given, I is a fixed, y is a linear, right? So bending stress distribution is linear. Shear stress distribution is quadratic. curved. Very important. So then I will plug in the number. So in this cross section, this on top, at the middle, where the neutral axis is, at the bottom are the, the location of interest, right? So then if I put this in the top, which is y is h over 2. So then if you put h over 2 here, what will be q? If y is h over 2, which is top of the beam, what will be q? 0. If q is 0, then what will be your shear stress? Zero. So as you can see from the formula, top of the beam shear stress is 0. How about bottom of the beam? If you put negative h over 2 here, then q will be 0. And if q is 0, your tau is 0. So top and bottom of the beam shear stress is 0. Then when we're gonna have q is a maximum? Middle. Whatever y is non-zero, this is a square term, so then this is positive, so then it will be decreased. So the maximum q will be when y is 0, which is at the middle. Which means, to summarize, your shear stress is 0, the top and bottom of the beam. Excuse me. And the maximum at the neutral axis. And we see a very interesting thing. When we learned in chapter 6, bending, we had a maximum bending stress top and bottom of the beam. And we had a 0 bending stress at the middle, right? But shear is opposite. We have a maximum shear at the middle and 0 top and bottom. And we can actually prove them mathematically from this formula. And also very interesting thing is from the statics, you learn that we have maximum shear when moment is 0, and we have a 0 shear when we have maximum moment, right? Same thing applied in the cross section. So everything makes sense. And when we have y is equal to 0, then q will be bh squared over 8, which is a maximum. So when you have this, when you have a maximum q, is it good thing or bad thing to the structural engineer? Do you want to have a small q or large q? Small, right? If q is large, shear stress is large, so then we need to have a more strong beam. So this is occurs at the middle. So knowing that, we plug that in. So then tau is VQ over IT. So then you put it here, and then everything is like that. And then again, tau is 0 when Y is top and bottom, and then when at the middle, tau is 3 over 2 V over A. Isn't this familiar to you, V over A? This is, when we have a, so when we go back to chapter 1, tau was a V and A. So then when we have the shear force applied in the given area A, we have a V over A, right? But this is a tau in beam. So this is what, 1.5 V over A, which is a 50% more than we have a direct application of the shear force on the given area, okay? So 1.5, which is 50% larger shear force at the neutral axis. So everyone so far so good? Awesome. Feel free to let me know if you have questions. Understanding this is very important. Of course, we will go over, together, solving problems, and then we will make more sense. But I want you to see like a physical meaning of, physical meaning of this, mathematical this mathematical formula, which is very important. And also, I'm trying to tie the shear discussion with the bending discussion, right? Because shear and bending goes together as a beam. Okay. So I summarized, bending and shear together here. So we have rectangular cross section BH, and what I'm drawing is, this is a cross section, and then this is a side view, okay? So this is a side view, and this is cross section. So don't get confused. And we know that shear stress is largest at in the top and bottom, and 0 at the middle, which is a neutral axis. But tau is maximum at the neutral axis and 0 at the top and bottom. And this is a linear distribution because this is linear function of y. And this is a quadratic distribution because q is a quadratic function of y.